So now that we've talked about the implementation, we visualized the hook methods, we looked at the implementation of the hook methods, let's go ahead and kind of take a step back and evaluate the pros and cons of this particular implementation, which is the search with parallel streams implementation. So let's look first at the benefits. So the real benefit, hopefully pretty clearly, is how little work was required to make it run faster. So here's the original implementation of, say, process stream. Here's the new implementation of process stream. Here's the only difference. That's pretty darn cool. So minuscule changes. But big speed up. So this is a version of the program running on an older version of my Windows laptop, which had a quad-core, hyper-threaded implementation with a fair amount of memory and 2.7 gigahertz processor speed. You can see we get a really nice speed up. But look at the actual numbers. So 1958 for the sequential version, 437 for the parallel version. Here's the same program running on my Mac, which had less memory but faster processors. And what you see here is that we get faster speed. So the parallel stream version ran faster than the Windows machine. The sequential stream version ran faster than the Windows machine. And that's just because the processors were faster, right? And this is a compute-bound processing. So all I'm just trying to show here is that the main difference will be how fast is your computer. And so you're not really limited by much else besides computer speed. Now, an interesting question, and this is a little bit outside the scope of the class, but it's interesting to think about, is why are we getting super linear speed up? So let's go back to this example. It's a little easier to think about. So this is about 2,000 milliseconds for the sequential processing. And then you look at this, and it's like 430-some milliseconds for the parallel processing version on a quad-core processor. Well, hold on a second, right? If it was really linear speed up, we would have expected to get this to be more like, it would have been expected to be more like 500 milliseconds or so. But it's faster than that. It's super linear. What's going on? Well, what's going on here is my laptops, and pretty much all modern laptops, are actually hyper-threaded. And so what that means is that they have these virtual cores. So even though it has 4 physical cores, each core is hyper-threaded. Well, what does that mean? So hyper-threading basically means that they will use what are called superscalar processing pipelines internal to the processor cores. And so what they'll do is they'll try to get more than one instruction executing during a clock cycle by simultaneously dispatching multiple instructions to different execution units. So they'll have multiple execution units, and they'll try to pipeline these things together. Now, whether this is a win or not depends on the properties of the data and your program. So it's not always a win. And it's definitely not going to be as much of a win as having more physical cores. But this is why we're getting super linear speed up, because there are also situations where they're using the superscalar architecture in order to get more things running per clock cycle. So just a little side note. Again, the real win these days is physical cores. The more physical cores and the better your programming language and your programming technique and your runtime environment and your hardware all work together seamlessly, the more scalability you get. And if you recall, I talked about this early in the course, that's why they moved Java towards data parallelism, because that has demonstrated itself to scale up better when programmed by mortals like ourselves, as opposed to super savant parallel programming people. So data parallelism typically scales better than parallelism based on more traditional approaches. Okay, but as always, it's not all rainbows and unicorns. There are some downsides. And the key downside, it's not really a downside. I mean, this is a big win, right? But the downside is this isn't the best way to get the system to behave. So even though it was simple, even though we only had to make these changes of stream to parallel stream, there are ways of making things run even faster. And in particular, if you look at the results here, you'll see that the parallel split iterator approach was the fastest way. That's really fast. And these other ones, based on completable futures, are actually a bit faster than the parallel streams version. Although, in this case, your mileage may vary a little bit. So if you were to run this on the Mac computer, which had less memory, the behavior was slightly different. So a couple things to note. There's, your mileage may vary. You need to benchmark stuff. You need to benchmark things correctly. We'll talk a bit more about benchmarking if we have time later in the course. But the main point is that just because we only had to make 2 changes didn't mean that was the best way to go. So we will talk later, and this will probably get us into next week, we will talk about this other implementation called the parallel splitterator. And the parallel splitterator is a splitterator that will take a given input string, like Hamlet, and it will break that input string up into chunks, because it's a splitterator after all, so it can split it up into chunks, and it'll typically split them up into about 4 chunks. And then it'll search for the phrases in each of those chunks in parallel. So rather than having one thread search the entire string, we will now break the string up into chunks and then have all the phrases searched for in those chunks as well. So it gives you yet another degree of finer granularity parallel computation, and as you can see, it gives you a bigger speed up. Now, the trade-off there, of course, is it takes extra work to write that splitterator. But once the splitterator is written and debugged, you get that win. And it's not horribly more complicated, although you'll see it is somewhat complicated. So those are basically the pros and cons of this example. And you'll see similar things when you look at your solutions for assignment 2 for the course, where the sequential version is very straightforward, modification of the original loop-based implementation, loop-based crawler. The parallel streams, one crawler, the first one you did for assignment 2B, not much different from doing the sequential version. You have to write a collector, but that's not too hard. And then the third example that you're doing, the parallel stream crawler 2, that has a more advanced, more sophisticated way of doing the parallel processing. So you hopefully get a win with each of these things that you're doing that will be more advanced.